Now we're recording. So we're going to do a quick impression of Euler calculating a flow line through a point for a given vector field with 5 steps in the delta t of 0.1. So what we're going to do is we're going to imagine the vector field as water flowing along a surface, and we're going to drop a leaf at the point 1, 2 and figure out where it's going to go. So at each step, we're going to do 5 steps, and then at each step, we're going to have a location and a direction. So at each step, we're going to have a location and a direction. So at the location 1, 2, our direction is 4i plus 1.6j. I just plug the 1, 2 into my vector field. So from the point 1, 2, we're going to go in the direction of 4i plus 1.6j for 0.1 units. So we're at the point 1, 2, and we're going to go in the direction of 4i plus 1.6j. So here's 4i plus 1.6j. But we're not going to go one whole unit. We're not going to go 4 and then 1.6. That would be 1 unit's worth. We're only going to do this for a 0.1. So we're going to go in this direction. I'll use pink for the x direction. I'll use t as 0.1 times 4 and in the y direction, I'll do 0.1 times a 1.6. So we're going in the direction of 4 and then 1.6, but we're not doing one whole version of it. We're doing 0.1. We're just applying the slope of 1.6 over 4 for a tenth. And then that's going to give us a new location here. So our second point is going to be at 1.4 and 2.16. So that's the next spot that we're at. So if we count this as x naught, y naught, then this would be the point x1, y1. That's our new location. Now we're at the location 1.4 and 2.16. So now our location is 1.4 and 2.16. So now we're going to recalculate our direction. So we're going to do 2.16 squared times I plus 1.6 times 1.4 squared times j. It's too early for me to do this just by thinking about it, even though I generally advocate for that. But that's just too much. And it says 3 decimal places. Whoa, 3 decimal places. So I'm going to carry 4 decimal places because I'm going to have to multiply by 0.1. I know I'm going to be multiplying by 0.1. So I'm just going to carry a lot of extra stuff. 4.6656i hat. And then 1.6 times 1.4 squared, 3.136 times j. So now I'm going 4.6 in the y direction and 3.136 in the j direction. That's going to be my slope, but I'm only going to do this not for this whole amount. I'm multiplying by 0.1. What was I thinking? Why did I keep so many things? Nobody stopped me. Minus 1,000,000 points for everybody. Just kidding. So now we're at the point 1.4 and 2.16, and we recalculated our direction. So it's going to go 4.6 in the I direction and 3.136 in the J direction. And that's going to be my point x2, y2. This is a continuation of this one. I didn't want to draw a whole big picture. So we're going in this direction, we're going 4.6656. And we're going 0.1. So in this direction, we're going to increase by 0.467. And then in the y direction, we're just going to do 0.1 times this amount, 3.136. And so in the y direction, we're going to increase by 0.314. So now our new location, if we do the 1.4 plus the 0.467, is a 1.867. I didn't need a calculator for that, but I used one anyway because it's early, and who knows what kind of crazy stuff I'm going to come up with. And then I'm going to take the 2.16 as my starting point, and we're going to add the 0.314. 2.474, and that's my new location. Now this is the point x2, y2. Next, now we're at this new location, so the vector field is going in different directions. It's changed in this massive 0.1 step that we've taken. It changes as soon as we step off of this point. But we're going to go in a straight line for 0.1 in both of these directions. But now our location is 1.867 and 2.474. And so our direction is just going to be the vector field evaluated at this point. And you can see where I'm going to bail on the problem. So in this case, we have to take, this has got us to step 2. We've got to go to step 3, and then step 4, and then step 5. And we need to be accurate to 3 decimal places. So we should be carrying more of these points. Sorry, more of these places moving forward. So my suggestion would be to do this by hand and take copious notes. That sounds like a pain in the butt. Or somehow encode this into a spreadsheet so you can do things automatically. That would be excellent. Any questions? But the idea is very straightforward. At every point x, y on the plane, there's a direction vector. So if we have a starting point of 1, 2, we calculate the direction vector and go in that direction a little while. Then we recalculate the direction at the new point and go in that direction. This will not give us an exact flow line. We're approximating a continuous flow with a bunch of line segments. But if we need to figure out where we're going to be after a little while, we can use this to approximate the flow line. Now, in a modern setting, this would be kind of a crazy calculation to perform by hand. We're not performing this calculation because it's important to be able to perform this calculation by hand, because in your future job as an engineer at, I don't know, fill in the blank, engineering firm, you're not going to be calculating this by hand. But we want to understand the process, and we want to, once again, approximate a continuous thing with a discrete thing. Approximate a curve with a bunch of line segments, because we do that a lot. That's what we're exploring, the connection between the discrete collection of line segments and the continuous curve. That's where the interesting stuff is happening. Any questions? All right, let's pause the video here and talk about other things.